In this first lesson, we're going to take care of some number basics and talk about classifications. We start off with a natural number set, which is the set we first learned when we started counting, like 1, 2, 3, 4, and so on. And they're all whole numbers, except for whole numbers actually includes the next number we learned about, which was 0. We learned in kindergarten or first grade about the concept of nothing, so we say 0, 1, 2, 3, 4. So the difference between those two sets is natural numbers don't include 0, whole numbers do. So whole numbers, it's got the O in there, so that helps me remember that it is 0 inclusive. And then later on in our math endeavor, we learned about integers, where we learned that there has to be negative numbers, like -3, -2, -1, 0, 1, 2, 3, and so on, in both directions. And we learned a lot more about those negative numbers maybe in college, I don't know. And then we've got rational numbers, which I'm going to have to erase here. Rational numbers are all the numbers that are in between all the integers. So all the numbers like 1.5 or 1.7. So to be specific, it's not just the numbers in between, it's very specifically the set of numbers that, so it's all fractions or decimals that, and specifically decimals, that either stop or they repeat forever. Okay? Now, this, for an example, we're talking about like 2/3. Okay, 2/3 would be 0.6666666, and it keeps going forever. And we put a line over top of it. Somewhere along the line, someone told us to put a line over it if it keeps going. Another example of this would be like 1/2, where the answer is actually 0.5. So you can see 0.5 stops, and then 0.6 continues to repeat forever. Those are examples of rational numbers. So fractions, which are turned into decimals that stop or repeat forever, which is contrary to irrational numbers. Irrational numbers are fractions or decimals that continue, that never repeat, but they go on forever. So we'll say decimals that go on forever, but with no repeat. So an example of that, of an irrational number, would be something like pi. Hopefully you've seen pi before, pi, which is 3.14, but it doesn't stop at 3.14, it just keeps going forever and it bounces all over the place. Another common example would be like the square root of 2. Okay, the square root of 2 has a decimal that doesn't repeat, like 1.142, blah, 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 and it keeps going forever and it never repeats, but it goes on. So those are examples of irrational numbers. And finally, we have real numbers. Well, real numbers are all the ones we've talked about so far. We finally call them real because they're tangible. We can use them for math. There's another number set called imaginary, but we're not going to be dealing with those in this particular course. So a graphic organizer for this would look something like, starting off with the natural numbers, and then outside of that, but including that, would be the whole numbers. Because we see that the whole number, if I draw a box around this, you can see whole numbers include the natural numbers. So the naturals are like 1, 2, 3. And the whole numbers start off with the same numbers, but they include 0 also. So they have all the same numbers, but it's inclusive and a little bit larger. And then just outside of that would be all the integers. And that includes everything so far, the natural, the whole, but it also includes the negatives, like -2, -1, ... And then just outside of that, but including all those previous, would be the rational numbers. Okay? And then, as a completely different set that's not inclusive, would be the irrationals. Okay, irrational doesn't fall into any of the previous categories, so it's completely separate. But then overarching and over top of all of this is the fact that they are all what we call real. Okay, so we've got this whole group on the left, and then finally on the outside we got irrational, and then over the whole thing we've got real. So those are our number sets, and we'll use this graphic organizer, going back to it, to identify examples of number sets when they ask us if they're integers. What we need to do, and you'll see an example like this in your homework, where we just have to identify which ones of these numbers in this set above are integers. So we have to pay attention to the description I gave earlier, which says that integers are really just positive and negative whole numbers, non-decimal numbers. So we look at negative 8. You want to look at 0. Then we look over here and we see 2. So those are the only numbers that fall into our integer set. And so what we do is we just write brackets and we say negative 8, 0, and 2. Okay. The next one asks for which one the rational numbers are. Well, rational numbers, if we go back to our set, are all the integers that we just previously said, plus more. Okay? So now we go back to this and we say, well, it's going to be negative 8, it's going to be 0, and it's going to be also the 2, but we need more. It's all the decimals that, or all the fractions that turn into decimals that stop or repeat forever. Well, to further my explanation earlier, 8.0, negative 8.0, stops. So that's why it's still rational. Okay? Square root of 5 doesn't. Well, negative 9/64 actually has a decimal that does stop. Or, in other words, I know that because it's represented as a fraction. If a number can be represented as a fraction, then you know for a fact that the decimal will stop. Okay? Or repeat forever. Okay? And then we see 0.5 here. It's a decimal that has stopped. 1/3 is represented as fraction. It's 0.333, and it keeps going forever. Now, this is 1.12. The line over it means that it repeats. So this one's also good. And that's it. There are no more. The other numbers that are left are not rational. So that means I would put down in a set down here, I'd have negative 8. Then I would have 9/64, and then I'd have my 0, my 0.5, my 1/3, the 1.12, and my 2. And I ran out of room for my bracket. So that's a set of rational numbers. Then the irrational numbers, ir means not, so the ones that are not rational are the leftovers. So negative square root of 5, square root of 3, and pi. So down here I'd say negative square root of 5, square root of 3, and pi. And finally, the real numbers. If I was to write the real numbers, basically I'd write this whole set again down here because they are all real. So now we need to talk about, first of all, the difference between interval notation and set builder notation. Set builder notation you're going to see in your homework, it looks like this. And then interval notation, you're just going to either have brackets or parentheses. I'll show one of each for each of these problems. So these are written in set builder notation. You'll see the x and then the line. Okay, what that means is we're saying that we're defining x, and then this bar right here means such that, and then the dot dot dot, it talks about something. So basically what we've got here is we're saying, alright, we've got x, and x is such that x is a natural number. So we're trying to define and describe x by the way that this bracket is written here. So we're saying that there's a number out there called x that's a natural number less than 4. And we're saying there might be more, there might be just one, there might be a few. So we've got to actually list, or hopefully not list, write an interval notation what those numbers would be that are less than 4 that actually fit for this description of x. So what that's going to look like is we've got less than 4 means not including 4. So we'd say, alright, well 4 doesn't count, so I can put a curved parenthesis, and we say all the numbers less than that, which would be comma negative infinity. And by the way, that's the infinity sign. This is the interval notation way of writing it. This means we've got all the numbers from negative infinity to 4. It kind of looks like a coordinate if you remember coordinates. But basically it's saying we've got 4, or we're not using 4, it's just less than 4, so everything up to 4. or another way you could say x is less than 4 like this, okay? And we're saying all the numbers up to 4, so it's like 3.9, but it'd be 3.999, 2, 1, 0, all those numbers. Rather than listing them out forever, the best way to write it is like this over here. This is interval notation. And so the curve means it doesn't include that point, like less than. In other words, it doesn't say less than or equal to. If it says less than or equal to, like this problem down here does, you're going to use the bracket. Okay? So, let's try the next one. The next one says x such that x is one of the first 5 even natural numbers. Okay? So, this time, the best way is to actually list what the first 5 even natural numbers look like. So we actually should write 2, 4, 6, 8, 10. And now this time we don't use the curve or the bracket because it's not using all the numbers in between. We're actually listing them. So I put them in a set. Okay? Finally, this last problem where it says x such that x is a natural number greater than or equal to 7 is basically looking like this. X is greater than or equal to 7, so we just have to write this in interval notation. Interval notation has, or would look like, starts with 7, and then x is everything bigger than that, so we're saying all the way to infinity. And because we are allowed to start with 7, we use a bracket on 7, and then a parenthesis, a curve on infinity, because you don't actually ever touch infinity. So we're saying the set goes from 7, comma, infinity. Okay? So now we're going to work on determining whether things are true or false based on the description we're given. This description says all irrational numbers are real numbers. And so what we should do is go back and look at our graphic organizer to see if that's true. And if you're looking at your graphic organizer, you see all the irrational numbers are under the subset that says real. So because they are, that is a true statement. So we write true, or we answer true on the lab. The next one says every rational number is an integer. So we should look back at our graphic organizer to see if that's true. And so looking at this, we're saying, all right, well, rational numbers are including the integers, which means that all of these numbers in the integer set are rational, but it doesn't work the other way around. It doesn't mean that all the integers go back and say that, or all the rational numbers go back and say that they're integers. It only works out. So that means that this is a false statement. So I say false here. Every rational number is not necessarily an integer, although all integers are actually rational numbers. You can't go backwards. Okay? So you work through some of those true or false statements using that graphic organizer. It makes it very helpful. Now we're going to take things that are in set notation and put them in set builder notation. Now the builder means that we've got this little guy right there, the x such that. So that means we got to take this set that's given to us and we have to describe it in terms of what x is. If I was defining a variable. So I rewrite this and say, first of all, I have to notice what's going on here. And I'm noticing that I've got odd numbers, and it goes from 1, 3, 5, 7, 9. So it looks like it's the first 5 odd numbers. So that's how I write it. I define the set saying x such that x is one of the first 5 odd numbers. Okay? The second set, it's saying I go from 5 to 10 to 15, so I'm looking at the powers of 5. So what I want to say here is I start off with x such that x is a multiple of 5 greater or equal to 5. And I added the last part because I just want to stray away from all the negatives, and I don't want people to get confused about 1. So I'm saying x such that x is a multiple of 5 greater than or equal to 5. So that's how you go from set notation to set builder notation. Now you're going to see some problems that talk about additive inverse. And so if you were given a number like 7 and you want to know what the additive inverse is, all you really have to know is what would you add to 7 to make 0? Well, all it is negative 7. Okay, so if it was like negative 20, and they're saying what's the additive inverse, in other words, what it adds with negative 20 to get 0, you just say, oh, it's 20. So additive inverse is whatever the opposite of a number. Okay, so nothing too complicated there, just wanted to describe that for you. And that's all I have for us in this first lesson.